Hello guys, how are you doing today? I'm going to record a really quick lecture and it's in 3D particle equilibrium. Last class we were dealing with 2D particle equilibrium. Basically what we did last lecture was we explained all the theory and all the basis about 2D equilibrium, particle equilibrium, and then we solved this problem. This problem was really interesting one. You can go back and review the lecture. But it was a really interesting one because instead of giving you the maximum weight that this system can hold, or the weight that this system can hold, and asking you for the particular tension in each one of the cables, the problem started like kind of backwards and gave you how much was the maximum weight if each one of the ropes could sustain a maximum tension of 200 pounds. So basically, the procedure is the same. You have to do particle equilibrium and isolate free body diagrams in every point that you can do that. And it's not that this problem cannot be solved by using rigid body equilibrium or 3D rigid body equilibrium, but the thing is that we haven't covered that part yet. So remember, the important thing about this is if you do particle equilibrium in 2D, the maximum amount of unknowns that you can have in each one of the equilibrium or free body diagrams are two, because you have two equations that you can use: summation of forces in X, summation of forces in Y, or summation of forces in any particular two directions. That's basically what you have to do. And what we did here basically was just that. We did particle equilibrium in all the points that we could, and then we did summation of forces in each one of them in X and Y, and came out with the system at the end. We didn't know how much was the weight, so we assumed that the weight was a known variable called W, and then we calculated each one of those forces or each one of those tensions based on the weight and came with the list. Important things to take out from this problem is that in engineering, usually when somebody asks you what is the maximum weight, like in this case, the maximum weight usually corresponds with the minimum weight, because it's the maximum weight per component. So if let's say that you start with this one and you calculate it in this one, and you say, okay, this is their equation of each one of the tensions based on the W. And if I calculate here my tension was 200 pounds. That was given. That's the maximum tension. That means that for this particular cable to withstand that 200 pounds, I have to calculate the weight, and that will be like 200 divided by 0.2679, 200 divided by 0.2679, and that's about 746. So for this cable to fail, that weight should be 746 or 747. Now what happens if I put that weight here and I say, okay, let me see how much will be the tension in this cable if I put that weight here of 747. If I multiply that now by 0.5176, that cable, the tension developed in this cable will be 386. That means that that cable is already failed because the maximum tension was 200. So that's what I'm saying. The maximum weight correspond, actually the maximum possible weight correspond to the minimum weight calculated in all of these instances. And go back to the previous lecture and review that because it was important. I suggested one extra credit. You have the extra credit already, and I posted the new one also, a new extra credit. So the next topic that I was dealing with was spring cables and pulleys. I'm showing some springs here, and what is the difference between including one spring and not including one spring? That you need to to work with the springs. You have done it before. So the only thing is that you have to apply the constant of the spring, or the stiffness of the spring, and the force developed is going to be the stiffness or the constant, that constant multiplied by the stretching or compression or stretching the formation, let's say, of that spring. And the other thing with pulleys also, and we work with pulleys, and remember the important thing about the pulleys, or the takeout that you have to get from this also explanation, is that if you have a small pulleys or frictionless pulley, this tension and this tension are the same. Now if you have friction, then you have to incorporate the friction here between the rope and the pulley, but we didn't cover that part in the previous lecture. And then I suggested this problem, which is a nice problem, and I explained it also in the lecture. You can go online and review it. It's a really nice problem. Actually, I have a model for that problem here, you see. It almost got destroyed now when I was explaining it to you, but you see, the problem looks like pretty much like this one here. You have a pulley here, you have the other pulley here with this spring at the bottom. The weight here, this weight comes from this side here, and this other weight comes around the pulley here with this other part here, and then you have the spring at the bottom getting measured the force here with this other part. So this is a setup that one student prepared for explaining this problem. You can try to do that also and see and corroborate and compare your measurements with that problem. I'm a fan of doing all the time these type of situations and explaining physically what is happening and showing physically, but we covered this problem also in the previous lecture. So today we're going to start with the same thing, 3D equilibrium, but it's going to be particle equilibrium in 3D. And what is the difference between 2D and 3D? I always say that 2D. So basically you're going to have, what is that? You see 3D equilibrium here, examples, funny examples, or whatever you want to call it, but the three-dimensional force system is exactly the same thing. The difference between 3D and 2D is 2D. What happened in 3D, now you have one extra equation because now you have x, y, z. You have a volume instead of a plane, so you have three components. But the way you do that problem is exactly the same way that you solve 2D. You draw a 3D free body diagram in this case. In the other case, we also drew a free body diagram. And then you apply the three scalar equation of equilibrium, summation of forces in three different directions. In our case, it's easier if you say x, y, and z. And from there, you can build up a system of three equations with three unknowns and solve for your unknowns. That's basically the same procedure every time. Okay. If a particle P is in equilibrium with 5 forces acting on it in the 3D space, how many scalar equations of equilibrium can be written for point P? I always ask this in class. I always ask this question in class. Say, if a particle P is in equilibrium with 5 forces, and as soon as I finish that, I ask, who say A, who say B, who say C, who say D, and everybody, yay! Because I just misled them, and the only thing they heard was 5. No, I already explained that, right? If it's in 3D space, you have three equations of equilibrium, a scalar equation of equilibrium, period. That's it. In 3D, when a particle is in equilibrium, which one of the following equations apply? Summation of forces in xi, j, and k has to be 0. Summation of forces as a vector has to be 0. Summation of forces in x equal y equal z equal 0. All of the above or none of the above? Well, these three equations are actually the same one. So the correct answer should be all of the above, because this is incorporating, for this to be 0, every one of them should be 0. For this to be 0, meaning it's in equilibrium, because this is in vector wise, and these are the same, basically. And these are the scalar equation of equilibrium. Once again, the three equations are the same. Applications. Well, we live in a 3D world. Some people say 9 dimensions, 11 dimensions, 23 dimensions, I don't know. To me, 3 dimensions and plus time, maybe I can understand. My mind is not as bright as some of the physicists, but 3 dimensions. That's what we're going to be working, x, y, z. For example, if you know the total weight here and you want to calculate how can you calculate the weight in each one of the cables? Simple. Do particle equilibrium, establish a system of 3 equations with 3 unknowns, and solve the problem. How do I calculate the distance here? How do I calculate? Well, 3D equilibrium once again in that point. And we're going to be doing that. Once again, the equations of 3D equilibrium are, we already discussed this in the previous conceptual quiz that I did. Summation of forces as a vector has to be 0, or each one of the components has to be 0, or the 3 scalar equations has to be 0. This is exactly the same thing. All of them are the same. It's different manifestations of the same figure. Example. Given the force F1, F2, and F3, okay, let me see, F1 is this one, F2 is this one, and F3 is this one. Calculate the force F required to keep the particle O in equilibrium. Okay, So important thing again, read carefully. When somebody is asking you the force F required to keep the particle O in equilibrium, this is not the resultant force, it's different. So there are two ways that you can do this. Either you calculate the resultant force of F1, F2, and F3, and then inverted no, calculate the opposite of that force, because if I calculate the resultant of these three forces pointing, for example, in this way, then the force that I'm looking for is the force that acts in the opposite direction to that one, like that, to make zero. I can do that, or I just can add this plus this plus this plus that and make that zero. That's basically the problem. How do we do that? Free body diagram is already done. Second, what do? Express each one of the forces in Cartesian notation. Big surprise, we have been doing every single problem like that. And then system of equations, three unknowns, and calculate for each one of them. Okay, let's start. F1, what do you know about F1? For F1, we know that it's working in the, look at that, look at this here, y direction. So it's gonna be positive y direction. 400 is the magnitude, so F1 is gonna be 400J because it acts in y. Now, what do we know about F2? F2 is this one here. Once again, F2 is acting in the z direction, but it's negative because this is the positive direction, negative direction. So F2 is going to be negative 800 K. Very well. Very good. 800 K. And now we have the force F3. Oh, we know the magnitude. Look at that. Coordinates of this point, coordinates of that point. Immediately when you see that, that is suggesting you to do what? Position vector. You calculate the position vector, divide the position vector by the magnitude of the position vector, and then you get what? The unit vector. You get the unit vector OV, and that unit vector OV you multiply by 700, which is the magnitude of the force 3. Remember, the unit vector is going to give you the direction, and the magnitude is given here, provided here. That is going to allow you to express the force 3 in Cartesian notation. In other words, you want to do that? Let's do that. Force 3, magnitude multiplied by the unit vector. How do you calculate the unit vector? The position vector divided by the magnitude of the position vector. Now, you can subtract the coordinates this minus that, which is 0, 0, 0 here, and the coordinates here in x are 3, no, in x is 2. You see, I got tricked by my own drawing here. So I say 3, no, this is not in x, this is in negative j. Negative j, so it's going to be negative 3. In this case, in an x is going back also, so it's going to be negative 2 and positive 6. When I subtract that minus this, I will get my position vector. Or you can do something that I call running the vector. For running the vector, you start from the tail and you go to the tip, perpendicular or parallel to the axis, and follow the same axis until you reach the tip of the vector. If you do that, look, I have to go to the left, negative 3 in j. I have to go back, negative 2 in x, and I have to go up, positive 6 in k. And that's exactly what we do when we subtract the coordinates. Negative 2, negative 3, positive 6. Now we divide that by the magnitude. What is the magnitude of that? The square root of this square plus this square plus this square. That's 7. And then I divide this by that. That's my unit vector. Multiply that by 700. And that would be my force number 3. Now you have the three forces expressed in Cartesian notation, F1, F2, and F3. What do? Well, you have to add those forces. I have a stamp here. Look at that. I just realized. I don't know how this came here. Okay. Yeah, it's a stamp. It was a US flag. Look at that. Look, I'm not kidding. That was what I had in my shirt. I was gonna be posted by mail somewhere. I don't know where. Okay. So we have the three forces here, and what we're doing is the summation of the force 1 plus the summation of the force 3 plus the summation of the force 3, F1, F2, and F3. And look, we have two ways. Either I calculate here the resultant and then switch the signs, or I add the resultant force F, which is not the resultant force. I add the force F in order for the summation of the four forces should be 0, 0, 0. What is the force F? I have no idea. That's what I'm looking for. But the force F, I know it has three components. x, y, and z. So that's how I'm gonna call the force F. Fxi, Fxy, and Fxc. And the summation of Fxi, Fyj, and Fzk. And the summation of these four forces has to be 0, 0, and 0. And I have my system of equations. And if you notice what I did here, I advise you to do that in every single problem. Be organized, one on top of the other, one on top of the other, and one on top of the other. This is not random that I left this space here, or this is not random that I left this space here. I know for a fact that the majority of you, when you're doing an exam, if you put that in line like that, a straight line, you're gonna miss one of those forces. And then you're gonna miss the exam and you're gonna get a bad grade, not because you didn't know how to work the problem, it's because you were just sloppy. So don't do that. Now, here I get my three equations. What is my first equation? Negative 200. Everything that goes in I has to be 0. So negative 200 plus fx equals 0. That's my first equation. Now I go in j. You see, one on top of the other. 400 minus 300 plus fy equals 0. And the last one is negative 800 plus 600 plus fz equals 0. I call it the system of three equations with three unknowns, but if you realize the solution is right there. So fx is 200, fy is negative 100, and z is 200. So if I want to calculate the force that keeps this in equilibrium, basically those are the components, so the force is going to be that one. If I want to calculate the magnitude of that force, I just take a square root of this square plus this square plus this square. Now if I want to get the direction of that force, what is going to express the direction of that force? The unit vector, or alpha, beta, and gamma, whatever you want to say it. So if you want the unit vector, you just get each one of the components divided by the magnitude that I already calculated. So 200 divided by the magnitude of f, 100 divided by the magnitude of f, and 200 divided by the magnitude of f. That will be the unit vector. And remember, if I do 200 divided by the magnitude of f, and I want to calculate alpha, I take the inverse cosine of that, and that will be alpha, beta, and gamma respectively. Okay, that's sufficient for that problem. Now the next problem, I used to do this in class, and I do like a group activity, and I ask the students to solve this problem after I explain the concept, of course. Then I have this problem for them. And this is a really nice problem because it involves different ways of decomposing the forces in Cartesian notation, or expressing the forces in Cartesian notation. Okay, the problem says here, a 100 kilogram crate as shown, this is the crate, is supported by 3 cords. One cord has a spring on it. Find the tension in each cord, well, in the cords AC and AD, and the stretch of the spring, not in each cord, basically. Tension here, and the stretching of that spring. I know this force here. Basically, look at that. How I'm going to solve that problem? You don't have to be a rocket scientist, right? How are you going to solve that problem? Decomposing each one of the forces in Cartesian notation, or expressing each one of the forces in Cartesian notation, and doing particle equilibrium, because this is the chapter that we are covering around this point here. And what are going to be your unknowns? Well, my unknowns are the tension in this cable, the tension in these cables, and the stretching of that spring. Or, because I know the constant of the spring, I can say easier that my unknowns are going to be the tension, and the tension. And after that, I can calculate the stretching of the spring. So that's exactly what we are going to do. Draw the free body diagram, express each one of the forces in Cartesian, apply equilibrium equation, and then calculate the stretching. Okay, a little bit bigger for you. Now, I have the 3 forces and the crate, and everything is in equilibrium, so I have to find that force, this force, and the weight. That's going to be my free body diagram, basically. And this is not complete, of course. Why is not complete? Because this is mass and we need it in weight, and I'm just doing emphasis in that because a lot of students mess up with that. A lot of students don't multiply these by gravity and then express the results in kilograms, and even though technically could be correct if you say kilogram force, a kilogram is mass, it's not a force unit, so you have to multiply by gravity. But I know that a lot of people lose points just by doing that. So multiply by gravity, and then you have your free body diagram. And I'm going to express here, I'm going to put here the original problem and the free body diagram. And then how are we going to solve this problem? Once again, the same way. I'm gonna start force by force. For example, force B. The only thing I know about the force B is that it goes in the I direction and it has only one component. How do I know? Because it goes only in the x-axis. So one direction, force B, there. In the positive direction, so my force B is gonna be FB magnitude multiplied by the I direction, which is the unit vector. Now, the force C is this one. What do you know, or what do we know about the force C? The force C, we know the cosine directors, the director angles. You have alpha, pay attention, this is alpha. What is alpha? The angle between the force AC, or the force C, and the x-axis, 120. What is beta? The angle, look, this angle is inclined between the y-axis and the force. And what is gamma? The angle between the z-axis and the force. What is the unit vector for this force? The unit vector for this force will be cosine alpha, I, cosine beta, in this case 135, J, and cosine gamma, which is cosine of 60, in K. What is the magnitude of the force C? I don't know it. That's one of my unknowns. But I know that I can express that as the magnitude of SC multiplied by the unit vector that I just described to you. Cosine alpha, cosine beta, cosine gamma, and that can be simplified to this one. What about D? What do you know about D? Well, I know the coordinates. Every time that you see coordinates over there, position vector, magnitude of the position vector, unit vector, multiplied by magnitude. Every time that you see alpha, beta, and gamma, cosine alpha, cosine beta, cosine gamma. That's basically why the problem is giving you those values. So let's do that. For this one, what are the components of this one? In X, -1, going back. In Y, +2, and in Z, +2. And this is 0, 0, 0. So basically that's gonna be my position vector. -1, +2, +2, -1, +2, +2, divided by the square root of this square plus this square plus this square, multiplied by my unknown, which is the magnitude of FD. And I get this equation. What is the last equation? The last equation is the weight. The last force. What is the weight? Well, the weight is acting downward and the magnitude is 981. That means that the weight expressed in Cartesian should be negative because it's pointing opposite to this one, negative 981 K. Now you have force B, force C, force D, and weight. And once again, I, J, K, one on top of each other. The summation of all of these, remember, equilibrium has to be 0. 0, 0, 0. What are my three equations? This is my first equation, this is my second equation, this is my third equation. FB minus 0.5 FC minus 0.33 FD equals 0. First equation. Second equation, negative 0.707 FC plus 0.667 FD equals 0, and the third equation is the summation here equals 0. System of three equations with three unknowns. How do you solve a system of three equations with three unknowns? I know, with a calculator, yes. I'm talking about by hand if you have to do it. Everybody says substitution, substitution, substitution. Think first and then act. Look at this. I can do it by substitution, but if you just look at the equations, look at the last two equations here. FC and FD has only two variables. And even more, look at this coefficient and this coefficient for FD are the same. So instead of using substitution, I use reduction or elimination. I just multiply one of them by negative. Imagine that I multiply this equation by negative, so this is positive and this is negative, and then I add these two equations. This is negative, this is positive, cancel out, and this is positive now because I multiply by -1. So this is going to be 0.707, 0.5, 1. If I add them up, this is going to be 1.207, and this passes to the other side, 981. And when you do calculator, 981 divided by 1.207, that's 812.76, well, 813. Once you have your value for FC from these two equations, I can get that, plug it into either equation, this is easier, and solve for FD. And then once you have FC and FD, you plug it in back here and find FB. Now, if I ask you, what is the problem asking you? Do you solve the problem already? No, you haven't. Why you haven't? Because the problem doesn't ask you the three forces. The problem asks you for two forces and also for the stretching of the spring. Two forces, this and that, we already calculated those, but the problem is asking me for the stretching of the spring. What is the big deal? I know the value for FB, I know the spring constant, and I know the equation that relates both of them. F equal Ks. From here, I can solve for the stretching, and once I solve for the stretching, I put my value for the force B, the constant of the spring. Careful with the units, kilonewton, newton, and I get my stretching in meters or in centimeters if you want. This is a really nice problem. I mean, combines different methods of doing particle equilibrium. You should definitely go and practice that problem again. Now, let's see what it says here. If a particle has 3D forces of magnitude 5 acting on it and is in a static equilibrium, the components of the resultant force are have to sum 0. Yeah, right? So negative 5 plus 3 is negative 2 plus 2 is 0. Let's see the second one. Have to be equal to 0. 0 plus 0 is, yeah, 0. Because the magnitude is 5, so the magnitude should be 5. No, because it's the opposite, negative 5. Which one is this? Well, every time that I poll my class about this, I get multiple type of answers. And I don't know why. 3D force, equilibrium, resultant force, 0. That's it. There's no resultant force. If it's in equilibrium, resultant force has to be 0. And a lot of people get confused here, and I add these three. How are you going to add I with J with K if they go in three different directions? You can't. So 3D equilibrium summation, or 2D equilibrium, or 23 dimension D equilibrium, if you know how to do that, because I don't, has to be 0. That's statics, right? Not dynamics. So 0. Okay, another problem. And this is a problem that sometimes I ask my students in class also as a pop quiz or extra activity in class. So it's a nice problem, but it's similar, extremely similar to the previous one, where the twist of this problem comes at the end. So what is the problem? A 150 kilogram plate. Okay, this is the kilogram plate. It's supported by 3 cables and it's in equilibrium. 1, 2, 3 cables. Find the tension in each one of the cables. How are you going to solve this problem? Same way. Do particle equilibrium. You can do this by doing rigid body equilibrium, but we haven't covered that yet. So the only particle that involves everything is right here, particle A. Of course, but the way it is acting here at the centroid, how I'm gonna translate or move that weight from here to here? Well, this cable has to be supporting the whole weight. So basically, it's like putting the weight acting up and doing this equilibrium here. What is the main objective? Converting each one of the forces in Cartesian formulation, adding with the weight, x, y, z, system of equations, 0, 0, 0, solve for each one of them. How are we going to calculate each one of the forces in Cartesian notation? What do I have here? Like distances, distances everywhere, no alpha, beta, and gamma, only distances, nothing else. Distances, coordinates, position vector, unit vector, divide the position vector by the unit vector, multiply by the magnitude, which are my unknowns, add them up and solve the system. Same procedure, same thing. So a little bit bigger here, you can have the 3 forces, and of course you need to calculate the components of each one of the forces here. You can calculate the coordinates if you want to, or you can add just run the vector. For example, if I want this force here, from here to here, and I run the vector, I'm gonna go from this point to that point, and I have to go in this direction. If this is my z direction and I'm going down, it's gonna be negative 12, and then I have to go in this direction. Oh, what is that direction? That direction is this one. I don't see the y here, but it was in the previous one. I just erased it somehow. But this is y, so this is going to be negative j. And how much is in negative j? 6 meters. And then I have to come from this point to this point. Oh, wait a second, the total distance here is 6, but this is 2. So if I go from this point to this point, that's going to be positive in the x direction, 4. And I do the same thing for the other ones. This is my free body diagram. I do the same thing. Look, I was working with B, right? I say 4 in I, negative 6 in J, and 12 in K. Divide that by the magnitude of the unit vector, the position vector, which is the square root of this square plus this square plus this square, and multiply that by the magnitude of force V, which is my unknown. Remember, the weight is 1472, and I should be acting downward if I put my weight here, but that wouldn't be a particle equilibrium. I'm saying that this cable, or these two cables, or this point has to be equal to the weight if this is an equilibrium. So the weight in my case is acting up like that. It's not the weight acts downward. It's not the weight, but it's the resultant here should follow the opposite direction of that weight. That's why, in the same magnitude. That's why I'm putting it upward like that. And this is not the difficulty with this problem. Once again, you come up with your system. This system, yes, you can do it by hand, but learn how to use it in the calculator. Go and I did a problem before, and I show you how to use matrices here. You have to create the matrix of the coefficients and the matrix of the independence term. Invert one, multiply by the other, and get the values. But there's a bunch of YouTube videos that you can browse on how to apply matrices to solve this system of equations, because doing it by hand is going to take some time. It's not that you can't, but if you have the tools and you can use them, use them. So basically, this is the component of the weight, because it's going only in that direction, but in the z direction. But the important thing with this problem is that then you solve the system and you find these results. And then when I always see that every single time, and when you find those results, everybody starts second guessing themselves. And it's good. I mean, second guess you is good. Not second guess you only. Interpreting your results. That's the good part. That means that this cable, the tension is 0. Okay, let's look at that cable. That cable is this cable here. How come that cable is going to be 0? Because my math set is 0? No, that's not the reason. So I like to play a lot with mental experiments and imagining these things, what is happening in real life if I have that. And you know, these two cables kind of look symmetric, but I can imagine, I can see it. And let's say that you can't see it. Look, you just build a tiny model of there. This is a tiny model. This is just a scale-up model of that thing. This is a piece of wood that I had, 3 cores over there, and I'm gonna use my tape to put it here on the top. And now, oops, it fell. Okay, it shouldn't fall. Now I have to go down and get that freaking tape. Come on, tape. Okay, here. This is live, guys. So now I have this situation here. You see, this is basically what I have over there. That means that if that cable is 0, and I hope it doesn't fall again, if I cut it, oops, it fell. Well, because it's not a scale, you know. But if that cable is 0, what is happening is exactly that. You see, that cable is not doing anything. It's falling and keeps falling, it keeps falling, but it's falling because the imperfection of the model. But this is what is happening. You see, the mental experiment works a lot better than the physical in this case. But if this is in the center of the weight, that thing should be kept in equilibrium like that. And the third cable is not doing anything except accounting for those imperfections, and that's why this fell in that part. As a matter of fact, if I scale this down with the original problem and I put some springs, equal springs here in this part, that's going to show that these two tensions correspond to the ratio that you calculated over there also in this part. Every time that you have a situation like that, try to come with a problem like that. What is the reason for that? Now, the reason for that is that if you look at these two cables, which are these two cables here, these two cables, if you look at those two cables are symmetric, and if you look at this base plate here, the two cables are one connected here and one connected here, and I joined those two cables with this line. You see that line over there? And the weight is exactly in that part over there. So basically what is happening in this case, if this is pressing like that in that point, this whole part here, this, you see, that's the reason it fell, because of this weight. I should have cut it here at the bottom and it could be standing. So basically this is like a triangular here, this triangle with these two forces and the weight, all of them are in the same plane. If there is any force acting on the one that I cut here, that should have also a horizontal component, and this thing will be moving in this direction, and that's not the case. So yes, the results are correct. If you can't see it, then build a model. And this is not my idea, building this model, by the way. I was teaching this in a lecture, and then the students, the next day one student came and he brought the model like this, and he used an old hard drive from a computer. I hope that he didn't destroy his computer to do that. And he was saying, oh, look at that, I put this here and I put this here. Of course, the weight was not like this one that could slide, so the weight was attached to that thing. But you know, guys, sometimes building a model, a physical model, is really easy. You don't have to go with any refinement to do that. And things like that, it failed, and this is life. I'm not gonna even edit it, because the same thing can happen to you, but somehow you can give the explanation and realize, yes, that makes sense, that that force is 0. At least I don't know if these values are correct, but that value makes sense, and that can give you a little bit peace of mind in that problem. So anyway, this is all for now. So next lecture we're gonna keep going with this, and next lecture we're gonna start, oh nice, next lecture is gonna be about moment. So we're gonna start chapter, what? It's the same chapter 4, but it's gonna be moment and in 2D. So that's a very important lecture. I'm gonna try to record it next week and make it available for you. Okay, guys. Bye, guys. See you later.